basically in mechanism postulation. It doesn't contradict it, so I could still be right. I need more information, but this is how kinetics helps to determine a mechanism. The SN1 reaction, when you study it, now this doesn't go through, the one I showed you here doesn't go through the SN1, but there are alkyl halides and conditions where when you study the rates, the rate depends on Rx only. When you change the concentration of the nucleophile, the hydroxide ion, for instance, the rate doesn't change at all. That's why it's called the SN1. It's first order in Rx. Cram this in. But zero order in the nucleophile. And so the mechanism symbol has to be SN1, and that has to be a different mechanism from the SN2. For some reason, there are two different ways of substitution. And the one that we're calling the SN1 is going through some reaction where only Rx is in the transition state. It only affects the rate as Rx. The hydroxide ion, or whatever the nucleophile is, never makes any difference in the rate. Concentration is irrelevant. And that's a different thing. So this is somewhat complicated. To make a long story short, what you're looking at here is that the so-called SN2 mechanism, as we now think clearly understand, is a one-step mechanism, sort of this bump and run type thing, where the hydroxide ion comes in and bumps out the halide ion in one smooth step. So of course it matters that you have both of these present. The SN1 is a different scenario where the alkyl halide dissociates into a carbocation plus a bromide ion. In other words, something causes the bromide ion to leave, and the culprit is not the hydroxide ion. What could cause that bromide ion to leave if it's not the nucleophile? Well, it could be any other collision, like with the wall of the container or a solvent molecule. There are other things that could cause a bond to break other than this nucleophilic attack of a hydroxide ion. The dissociation, though, of ethyl bromide into something as nasty as a free carbocation is a very slow event. But it would make sense that if you get some carbocation in there, that could react very quickly with hydroxide ion to give the same product as the SN2. Now, in chapters 6 and 7, Volhard and Shore spend a lot of time trying to get you to see this. So you can save yourself a lot of time by seeing it now. The difference between these two mechanisms is timing. When does the bromide ion leave? Does it only leave when the hydroxide ion shows up, or does it take off ahead of time? If it waits for the nucleophile to show up, that's the one-step SN2 mechanism where the rate is second order. If something happens separately, nothing to do with the nucleophile, to cause the alkyl halide to dissociate, so the leaving group just walks away, seemingly on its own, and then the hydroxide ion grabs the carbocation, this is going to be the rate-limiting step, the formation of the carbocation. When you have two steps, the slow step is the rate-limiting step. The slower step is the rate-limiting step. And you would readily accept, without any experimental data, that having ethyl bromide fall apart is a lot tougher than having that ethyl carbocation grab a hydroxide ion. That's what we call a trapping reaction. So it's instantaneous. Yes?
So SN2 waits for the hydroxide ion to come?
Yes, the ethyl bromide is intact. In a sense, that's the normal case. Everybody is patient, waiting for the hydroxide ion to do its thing and push out the leaving group. And so that rate depends on how much ethyl bromide and how much hydroxide ion you have. It's SN2. The SN1, the rate is determined by how fast the carbocation is produced. The second step is totally unrelated to the rate of the process. So it doesn't matter how much hydroxide ion you have, the rate limiting factor is ethyl bromide. So to the extent that it's going to go through the SN1, the two-step, the rate is only dependent on ethyl bromide. Yes?
Would that same reaction be able to take place with like chlorine or chlorine?
Yes. Right. Same thing always happens with either one, just at different rates. And in fact, remember, you run a reaction with a lot of chemicals. You don't just take one molecule of hydroxide ion and one molecule of ethyl bromide and put them together with molecular tweezers. You've got this universe of zillions of molecules whizzing around. Some of them can go through the SN1 path, and some of them can go through the SN2 path. So these two different mechanisms can be going on at the same time. Now you would say, well, who cares? Both produce ethyl alcohol. And in fact, that's true. It's purely theoretical. Now there is a case where it matters, and it has to do with stereochemistry. So we're going to have to deal with that. But if it's not a matter of stereochemical difference, and ethyl alcohol has no enantiomers or diastereomers, it has no asymmetric carbons. The only time it matters is if the carbon attached to the leaving group is asymmetric and it has a particular configuration. That can be disturbed depending upon whether it's SN2 or SN1. And we'll talk about that. But for the moment, just understand that this other path here is the SN1. Now what students always get, or almost always get reversed, is that the SN2 is the one step, and the SN1 is the two step. It sounds backwards, but that's because the SN1 has nothing to do with the number of steps. That's the rate data. It's first order in ethyl bromide or RX. The 2 in the SN2 doesn't mean two steps. It means it's what we call a bimolecular reaction. Two molecules have to come together in the transition state for the step, rate limiting step. So don't confuse that. The SN1 is a two-step that goes through the carbocation. The SN2 is the one step. Now, these two mechanisms are not really competitive because of carbocation stabilities. If you have a carbocation, the stability of carbocations depends on whether it's a tertiary, secondary, or primary carbocation. This one here is a primary carbocation because the plus charge is on a primary carbon. And you notice I've got double arrows between tertiary, secondary, and primary. That's because I want you to recognize that there's a big difference in stability. This isn't minor. But be careful. All carbocations are bad news. All of them. But within the family of carbocations, some are much worse than others. The primary carbocation is the least stable. The secondary is much better, and the tertiary is much better, but all of them, in general terms, are nasty. Since the SN1 mechanism requires the production of a carbocation, what type of alkyl halide would be most likely to go through an SN1 substitution? Okay, tertiary example would be this. And a primary would be this. When the tertiary bromide ionizes to the carbocation, you do produce a bromide ion, but you also do from ethyl bromide, so that's a wash. How quickly these two alkyl halides form carbocations obviously depends on how stable the carbocation is. So which one is more likely to fall apart? The tertiary, right? Because that's going to form a more stable type of carbocation. The SN1 depends on producing a carbocation. The tertiary halide produces the best type of carbocation. So that's the one most likely going to go the SN1 pathway. The primary is the least likely. So if you have a tertiary halide, SN1 substitution is very likely. If you have a primary alkyl halide, SN1 is very unlikely. The secondary is the gray area in between, and it is a gray area. Now, what about the SN2? Well, if that has to come in and force out the leaving group, what kind of alkyl halide would you think would be most able to undergo this SN2 process? Tertiary, secondary, or primary? Primary. Why?
It's only connected to one other carbon.
Right. What difference does that make?
Reduces, I guess, difficulty in pushing the halide out.
Right. There's a crowding problem there. The SN2 requires the nucleophile to get real up close and personal to the carbon with the halogen. It's got to get within bonding distance. Now, what it's actually doing is grabbing. So here's the bond to the bromine, and these bonds to carbon, you've probably forgotten about it, but there's a little back lobe on the carbon. An sp3 orbital is a teardrop-shaped orbital like this with a little back lobe. and the carbon's right at that cross point. What the nucleophile is actually doing is coming in and latching on to that little back lobe. So it's almost like if you use a napkin with a napkin ring, like it's on one side, you grab the other end and pull it through. The hydroxide ion is grabbing that little back lobe and yanking the rug out from underneath the bromine. It's actually pulling the bond to the other side. And there's evidence for that we'll show you next time, but it's actually described as an opposite side attack where the nucleophile has to come in not only really up close to get that little nub of a back lobe overlap, but it's the opposite side of the halogen, and then the halogen just kind of drifts away because it's had its bond pulled away from it. So that's very sensitive to crowding around that carbon. And a tertiary halide is like this one right here. If you make a space-filling model, you can't even see that carbon that the halogen's attached to. It's just buried in these big grapefruits that are the 3-methyl groups. So there's no way that that tertiary halide can undergo the SN2 substitution. The primary, on the other hand, ethyl bromide as an example, that's much easier because it's got 2 hydrogens which are small and just 1 carbon. So after the carbon with the leaving group, there's a minimum of crowding. So for 2 reasons, these are not really in one another's way. The SN1 and the SN2 don't fight with each other. The SN1 works best with a tertiary because the tertiary can form a carbocation best. And the SN2 isn't bothering with it because there's too much crowding. So there's no competition. It's perfectly set up for the SN1. The primary is perfectly set up for the SN2 because while there isn't much crowding here, also piling on is the fact that it doesn't want to form a carbocation. So it's ignoring the SN1 mechanism and letting the SN2 door open. The secondary is stuck in between and can go with a mixture of the mechanisms typically. And a lot of what's in chapters 6 and 7 is talking about this and a host of other factors that can tip the mechanism through the SN2 or the SN1. The reason I mentioned this business of stereochemistry, if you have an asymmetric carbon with the leaving, where the leaving group is, and let's say it has the R configuration and it's 100% optically pure, really valuable. Like it's an amino acid, for instance, with a definite configuration at that carbon. When the nucleophile does that SN2 substitution, it has the same effect as an umbrella converting in the wind. Now, some of you may have experienced that during the storms that we've had, but when that wind catches your umbrella and turns it inside out, that's like a mirror image of your umbrella. So
The windshield
when
wipers.
the nucleophile
I freaking like.
reacts with a chiral carbon and pushes out the leaving group, it goes from R to S or from S to R, creates the opposite configuration at that carbon. Now it keeps the optical purity because it's always doing that inversion. So if you had 100 umbrellas, they're all going to invert. So you don't lose the optical purity, and you can't actually predict the result. So if you run the reaction with the right starting material, it's actually a chiral reaction. The SN1, on the other hand, goes through a planar carbocation. So if you have a chiral carbon, it forms a flat carbocation. And then the hydroxide ion can attack that carbocation with equal probability from either face. The top face, if the three groups go down, your umbrella folds one way. If the hydroxide comes in, your umbrella folds the other way, and you get a racemic mixture. So the SN1 is bad news if you have an asymmetric carbon that you're trying to work with attached to the halogen. But that's the only case where it matters. Otherwise, it doesn't matter at all. Okay, let's stop there.